Okay. Dear colleagues, you see the speaker today is Dr. Bekzat Zhakhayev from the University of University in Kazakhstan, and also from the Institute of Mathematics and Mathematical Modeling in Almaty, Kazakhstan. His talk is Varieties of left-commutative algebras. Okay.
Thank you. Today I want to talk about varieties of left-commutative algebras, namely proper varieties, bicommutative algebras, and varieties of Novikov algebras. So let's start. So first we define. Also, let's give a definition of variety of algebras. So let this Kx is absolutely clear non-associative algebra. It is a set of polynomials in the algebra. The class of algebras satisfying the polynomial identities, each, and is called the variety of algebras defined by the system of polynomial identities. And a variety of algebras is called subvariety of the variety of algebras M1 if M2 is a subset of M1. For example, variety of bicommutative algebras and the variety of all Novikov algebras are subvarieties of the variety of left-commutative algebras. Let's give definition. So here, oh, sorry. In future we use lattice of subvarieties, and so the set of all subvarieties of variety of algebras forms a lattice. We denote by the symbol. With respect to the operations, so this join and meet for all M1 and M2 from the set. And the lattice is called distributive if satisfies the following identity for all M1, M2, and M3. And in this work, here we can see that the distributive of lattice of subvarieties is equivalent to the condition set in co-character sequence. So here, co-character sequence, and here K lambda is irreducible character of Sn representation. So all multiplications satisfies the condition up to 1. So Bokut question. In 1976, Leonid Arkadyevich Bokut formulated the following question. So this to describe in terms of identities. Above we considered identities, polynomial identities, varieties of rings for algebras whose lattice of subvarieties is distributive. And in this year, Ananin and Kemmer in this work described the varieties of all associative algebras with distributive lattice of subvarieties. And 1982, Martirosyan found a criterion for distributivity of the lattice of subvarieties of the varieties of all alternative algebras. And 1984, Martirosyan found distributive condition for right alternative algebras. So here, this works of Martirosyan and that is topics. So what is left-commutative? An algebra is called a left-commutative algebra if it satisfies the left-commutative identity for all elements that we see from algebra A. So this algebra first appeared in the work K in 1857. So you can find this work here. So this algebra. So now we consider varieties, subvariety of the variety of all left-commutative algebras, this bicommutative algebra. And then this algebra is called bicommutative if it satisfies the identities. It is we call right identity, right commutative, and this called both left commutative for all elements ABC from the A. So we denote by this symbol variety of all commutative algebras. So bicommutative algebras first appeared in a work Jumadlev and Tulimbayev. In this work, authors proved square of bicommutative algebras is commutative and associative algebra. And in this work, Jumadlev, Ismailov, and Tulimbayev constructed a free basis for bicommutative algebras, calculated co-dimension sequence and the co-character sequence of free bicommutative algebra. And in 2018, Drensky and V solved positively solved the Sheff problem for the varieties of bicommutative algebras. And so we shall describe the varieties which satisfy one of the identities. It is first our identity of degree 3, and the second our second identity. The results we will be given in the language of graph theory, because lattice of subvarieties is described in the language of graph theory. So lattice is a graph is an element of graph theory. Our approach is similar to the approach like Vladimir and Drensky in this work, whereas after describing the varieties of all associative algebras satisfying a polynomial identity of vertical. Well, so in this work we use a basis of free bicommutative algebra, and we denote by this symbol GD of B, which is described in this work. So Noetherianity and the Sheff problem for varieties of bicommutative algebras. So let be a polynomial algebra into the variables, and let this and this be augmentation ideals of this and this respectively. Then the algebra GD has the following basis. So XD is the set of generators, union, and this monomials. This monomials is described in this following way. So one YD, all this Z1 and so on ZD, all these generators from the set of XD. So and the multiplication be given by following way. So Xi Xj product we define by Y I Z J, and if we product from the left side to this monomial, we get this monomial. If we take multiplication from right side, we get this monomial, and if you take product of two monomials, we take this monomial.
We see this, we see this, but the public online cannot see that because they see what is there, not in the. So simply have in mind that when you show, we see this, but the public online doesn't see. So when you see this and this, they don't know what is this.
Okay. So example, let n is equal to 3. There are two typical bases in non-associative forwards. It is space of multilinear polynomials of free bicommutative algebra of degree 3. So has the following values: ABC, BAC, CAB, and in VCA, ACB, and ABC. And we rewrite this all basis elements in the following way. So in this element, we correspond to this element to correspond to, and so on. So highest weight vectors. So the highest weight vectors of GL dim submodels. So it is way more this of free bicommutative algebra. We describe it in this work. So in lemma from this work, and it says that, and therefore Boolean polynomials W lambda K for maximal linearly independent system of highest weight vectors of them submodels in GT squared. So first class of highest weight vectors will define this way, and the second class will define this way. So here all lambda 1, lambda 2 is part of partition, lambda, and corresponding to Young diagrams with partition lambda 1 and lambda. So our goal in the study of bicommutative algebras, describe all subvarieties first. Thus, describe all subvarieties of the variety of bicommutative algebras, defined by identities of degree 3. And the second, investigate Bokut's question for the variety of bicommutative algebras. So we need to answer these questions. We need a set model structure of free bicommutative algebra, and set model structure was investigated in the work to my Vayev. And the theorem says that multilinear component of free bicommutative algebra is isomorphic to this decomposition. Here, M lambda is a Specht model. Sometimes, yes, sometimes we call Specht model, and or we call irreducible SN submodels for partition lambda. Here our sum goes by all lambda. Lambda is a partition of number n with two parts, and M lambda is the multiplicity of the model, and defined by this following rule. So when n is equal to 1, lambda, multiplicity is equal to 1, and when lambda is partition with one part, then multiplicity of corresponding Specht model is equal to n minus 1, and when Specht model, multiplicity is equal to this value, if lambda with two parts, when the second part is positive, is not equal to 0, more than 0. Then, for example, in degree 1, we get following decomposition. In degree 2, we get following decomposition. And in degree 3, we get following decomposition. Here, it is trivial irreducible model, and with multiplicity 2 by this formula. And this two-dimensional irreducible model of FSE has the multiplicity 2. So our aim, the irreducible S3 submodel M3 is generated by this polynomial. Here, x with a bracket xx is generator of one of them here trivial model, and the second one is second generator of this corresponding trivial model M3. And the alpha 1, alpha 2 is any coefficients with this condition, and here n irreducible submodel is the third model generated by this polynomial. Okay, so case 1, because to answer our question, describe all subvarieties of the variety of all bicommutative algebras of degree 3, we need to include additional polynomial identities. So, and So here, so all in the here. So below we present all results from the paper. So let the U alpha would be the subvariety of the variety of bicommutative algebras defined by this identity. This one, which generator of this model. So then we have some cases. First one is a general case. So this general case, and then proposition says that when alpha 1 product of alpha 1, alpha 2, and the alpha minus 1, alpha 2, and the alpha plus alpha 2 is not equal to 0, we have following decomposition. So here we write in character language. So here n starting from 4, all participants in decomposition is isomorphic to 0 model. And here theorem says that. So when the condition is false, the consequence in relatively algebra of degree n plus 1 of the polynomial corresponding to partition are equivalent to the following polynomials. So for W1, so it means that it is highest weight vector. It is the polynomial with x1, and this polynomial with this one, with this with y1 and z1, and this. So for we have following consequences, and for this generator and the polynomial, we get following consequences. So and the polynomials this and this do not have a consequence of degree 4. We illustrate this theorem in the following figure. So here. So F1 is this generate highest weight vector. F2 is this one. F3 is and this one, and G1 and H3 is respectively. And so we get following lattice of subvarieties. And here is stated in the language of theory. So points means that generators of our irreducible submodules corresponding degree, and this arrow means that F2 follows from 1, F3 follows from F2, and the G3 follows from F2 and the G2, and so on. So case 2, so alpha 2 is equal to 0. Then proposition says that we have following model structure. It's a model structure, and starting from 4, our decomposition has following view. N1 is this trivial model, and it is n minus 1 dimensional model, irreducible. And this model generated by this highest weight vector, and this model generated by this highest weight vector. And we get following consequences. So so here identity of degree 1 or 2 implies all polynomials of degree n3, 2 and 3, and the identities, so this and this implies this polynomials of degree 4, and this and this imply this and this polynomials of degree imply n plus 1 respectively. So polynomial this doesn't have consequence of degree 4. So illustrated in the following way. So we have following figure. F1, F2, F4 defined in this way, and the G2, G3, G4, Gn defined by this highest weight vector, and the H3 defined by this highest weight. So we have following picture. And the case alpha 1. This case is similar to the case 2, and we here we skip next condition. Alpha sum of alpha 1 and alpha 2. And we have following model structure of relatively algebra for alpha. Alpha means that this condition is satisfied. And so in degree 4, we have 2 irreducible models, and in degree starting from 5, we get only trivial representation or SN models, SN submodel, irreducible SN submodel. And the corresponding generators for this model is defined by highest weight vector N1. And then, so here we get following picture. So this picture says that so F1, F3, 4, 5 defined by these highest weight vectors, and G2, 3, 4 defined by this. So we get following picture, and so P4, so it means this highest weight vector also identity. This identity follows from the F3, G3, and the H3, and so on. Case 5 says that starting from 5, we get we have this co-character sequence. Means that is an impotent, and we get this picture. So starting from 5, there is nothing, and so theorem says that degrees, identity of degrees 1, 2, 3 implies the polynomials of degree n plus 1, and then this identity doesn't have any consequence of higher degree. So it means G4. G4 is this one, placement. So next group of cases, and beta 1, beta 2. So we know this polynomial. It is generator of our irreducible S3 submodel for partition 2, 1. And we denote by this symbol the subvariety of the variety bicommutative algebras defined by this identity. And then proposition says that in general case, we have following sequences of characters. So in degree 4, we get this decomposition. In degree starting from 5, we get only this decomposition. And here, this partition, irreducible GLD submodel, this and this generated by respectively by this identity, this one and this one, and this generated by this highest weight vector. So then we have following consequences. If W1 has a consequence this polynomial and this identity, and this identity has following this and this, and for example here is a definition. For example, for this identity we have following this identity consequences, and for example for this identity we have there are no consequences of 5, and for starting 5 this identity has a consequence this identity, and the case 1 is treated in this way. So here F6, F7, F8, and so on. So all F1, F2, Fn generated by this polynomial, Gn generated by this polynomial, H1 this, In, Gn corresponding by this polynomials. So next, B2 is equal to 0. We have following co-character sequence, so decompositions. And here, starting from 3, we get always 2 multiplicity in as of trivial model, submodel, irreducible. So, and the corresponding generators for this model is this polynomial and this one. For this model, we the model has following generator, and so then we get all these consequences, and the theorem. So in picture, this we get this picture of all the consequences. So F1, F2 generated by this, and the Gn is generated by this polynomial, H1 this, In is the difference of 2 polynomials, Jn is a linear combination of 2 these generators, and so, and the B1, the case B1 is equal to 0, is similar to the case B2, and we can omit. And B1 plus B2 is equal to 0. We have following co-character sequence. So, and then correspondingly we get this idea of all consequences of degree n plus 1. And so in last our condition beta 1 minus beta 2, we have following decomposition. In degree 4 we have multiplicity 2, and starting from 5 we get multiplicity up to 1 here. So and then in result we get picture of consequences. Here F1 defined by this polynomial, Gn defined by this polynomial, H1 by this, In, Gn corresponded by this and by this polynomials. So here, between G4 and the H3, there is no error. In that, G4 is not consequence of H3. So, here, theorem says that variety of any variety of bicommutative algebras has a distributive lattice of subvarieties if and only if it satisfies the identities. It is generator of our trivial models and the generator of second dimensional irreducible submodel. For some pair alpha 1, alpha 2, beta 1, beta 2, which is not equal to 0, 0. And here we list all list consequences of subvarieties. Sorry, description of subvarieties defined by degree 3. Whose lattice of subvarieties is distributive distributivity. So here, in general case, we get this picture. So starting from degree 4, our codimension sorry, character is equal to 0, and here was the second case, and in this case we get this picture. If you notice it, all this, all FN, it is generator of our one-dimensional irreducible model, and here n-1 dimensional irreducible model, and here too, F1 generate one-dimensional irreducible model, and here others, for example, G2 means here G2 is generator of model with partition 1 and 1, and the K3 is the combinations of two-dimensional irreducible model submodels. So here, when our condition is alpha 1 minus alpha 2 is equal to 0, we get this picture. So starting from 4, all our character sequence, all generators of our irreducible submodels is equal to 0. And yes, all five figures. It is full description of all subvarieties of the variety bicommutative algebras of defined by degree 3. Yeah. So it is answer to the Bokut question. Second, our second subvarieties of the variety of left-commutative algebras is Novikov algebras. So algebra is called Novikov algebra if it satisfies the two identities. First one is the right symmetric identity. Second one is the left-commutative identity. Here, bracket x, y, z means z, the associator of elements x, y, and z. So the term of Novikov algebra was coined by Osborne and Marshall. And so we denote all variety of all Novikov algebras by this symbol. And here example for Novikov algebras. So it is polynomial algebra in one variable x, and on the algebra we define new operation, new product multiplication operation, and this multiplication operation defined by this way. So it means that f prime g prime is a derivation. So then the pair is a Novikov algebra. So Novikov algebra was first appeared independently in the works, example 1970 by Gelfand and Dorfman works. Here studied Hamilton and operator in finite dimensional mechanics. In 1985, Valinsky and Novikov studied relations in the equations of hydrodynamics. In this work, Drensky constructed a basis for free Novikov algebras in the language of Young diagrams. In this work, Drensky Ismailov investigated, maybe in other words, full described SN and the general model structures of free Novikov algebras. And in this work, Drensky Ismailov positively answered to the Speck problem for the validity of Novikov algebras of a field of zero characteristic. In this work, we use the basis of free Novikov algebra. So we denote our free Novikov algebra by this symbol, which is described in these works. And using value number 5. In these works, basis of free Novikov algebra constructed in the following way. So xin I2 xin, all these generators of the field algebra, and this in power k1, k2, kn means the number of derivations, and its sum of is equal to n minus 1. So, example, in non-associative words, multilinear component of free Novikov algebra has the following values. This values, sorry. And in differential monomials in this language, we get following values: A2 primes, BC, between all two these values we have corresponding. So it corresponds to this monomial, and this corresponds to this monomial, and so on. So we use these values. It is coming for our calculation. So as a model structure, in this form, the method is made of give full description as a model structure of free Novikov algebra, and this theorem says that multilinear component is equal to as isomorphic as a model to this decomposition. So here m lambda is the irreducible S n plus 1 submodel corresponding to partition lambda, and m here k lambda omega nu, it is Koszta numbers, and the omega nu means that width for partition mu. So, for example, when degree is equal to 1, we get this decomposition, and when n is equal to 2, we get this decomposition, and 3, we get decomposition with here one trivial irreducible model has a multiplicity 2, and here two-dimensional irreducible submodel has a multiplicity 2. And this model generated by this polynomial, and this model with multiplicity 2 generated by this polynomial. And we get following cases. So here in case of Novikov algebras, we investigate Bokut's question for the variety of Novikov algebras. So, and here below we present results from this paper, and we introduce this subvariety of the variety of Novikov algebras defined by this identity. So then we get following theorem. So alpha beta is equal to 0, 1. We have following decomposition, and correspondingly generators. It is polynomial generates this model, and this polynomial generates this model respectively. And when alpha pair is equal to 1, 1, we have following decomposition. So here, for example, starting from 6, we get 0. And in degree 4, we get following decomposition. In degree 5, we get this decomposition. And all this generated by the following polynomials. So this one generated by this polynomial, this one generated by this one generated by this one generated by this, respectively. And when alpha beta, this pair is equal to this pair n1 and minus 1, we have this decomposition, some more decompositions. And all this generated by this polynomials, respectively, and otherwise we have 0. So in following the case when gamma and the delta. So we introduce this symbol. Here, this is a subvariety of the variety of Novikov algebras. Here, gamma delta with this condition. And we get following co-character sequence. The 2 times mn and the m and minus 1. So when the pair is not equal to this 0 and 1, this modus generated by linearization of these polynomials. So when 0, 1, we get following polynomials. And case 3, it is a here we take we take 2 polynomial identities, alpha and beta. We consider together, and we denote this subvariety by this symbol W rho, and we get following co-character sequence. For this case we get this decomposition. For this case we get this co-character sequence, and for this case we have this character sequence, and in all other cases we have this co-character sequence. So then in result we get the lattice of subvarieties of variety of Novikov algebras is distributive and only if all algebras of that variety satisfies the identities this and this with condition alpha beta gamma beta from this space. So we can illustrate. Let's illustrate all these cases. Sorry, this case rho, and we get following by and 1 and 2 and 3 all these generators. Sorry, one-dimensional irreducible models. Trivial model, and here all here n-1 dimensional irreducible submodels, and here we do by this consequence of this model, and this model is consequences of this model, and so on. And here, when 1 minus 1 and 1 and 0, we get following picture. And in this case, 1, 1 means that alpha is equal to 1, beta is equal to 1, and the gamma is any number, and delta is any number. We get following picture of consequences. And in all other cases, we have following by the web. So, and by all this picture, we answer to Bokut questions about describe all subvarieties of the variety of algebras whose lattice of subvarieties is distributed. So, thank you.
Do you have any questions?
No.
If not questions, okay, maybe we finish. So I think we want to make a small comment about this. You see here, these objects here appeared in the theory which is quite far from algebra. You see that in thermodynamics, quantum mechanics, etc., etc. So the original was in another place, but the people who developed it, they're non-associative. So they can do everything in the language of non-associative algebras. With Bekzat, we started doing something with commutative algebra, that the square of the algebra is commutative and associative. So all the machinery of commutative algebra, which for example is old, it should work. So all the things we do, we translate in the language of commutative algebra and show that many things they follow almost automatically. And they follow difficult if you do this in the non-commutative algebra, but clearly it is commutative algebra. So this is something which was very, very nice that if you were like non-commutative problems, non-associative problems with classical theorems in
May I ask one very stupid and light question? So the title contained left-commutative. It does mean that you can literally follow the same things to do for a right-commutative, whatever it is.
You see bicommutative there, both the left and right.
Yes.
And Novikov algebras which appeared in the paper by Kelly in 18 something. He studied algebras which one-sided commutative. But you can do exactly the same, replace left and right. This is the same as a ring theory. Not ring theory, you have left theory, you have left ideal and right ideal. If you do something for left ideal, so much you can do the same for right ideals.
So in this case, how the statements change? So they're
Okay, in algebra you have commitment, you have isomorphic and anti-isomorphic. So isomorphic, this means that they are the same, and anti-isomorphic, you change the order.
Yeah.
So this is.
Here we can see the right Novikov algebra. If you introduce a new operation, A product B, A product B, B A product, you can take left Novikov algebra. Left Novikov means that left symmetric identity and the right commutative identity.
You see, your number which was left-handed, and here are everything from the other side, and the other to read what's the other, you don't to see in the mirror. We have something similar here, if you want to do, you should see. But with the Young diagrams, it's even worse, because when you use Young diagrams in France, you should see mirrors on your head down.
You should do your push-ups. Can you find some interesting symmetric functions or bases?
Okay, if you speak about PI, the number of identities,
Yes.
there are many things which are difficult in the associative case, for example. They are here very easy because you use the human basic theory for 50,000 work.
Okay.
Or some other result which are considered representation theory, the general linear look on the spectrum group, you also have everything.
Yes, but maybe you have a special class of symmetric functions that come as bases, natural highlighted bases of those Novikov algebras. Maybe. Don't know.
Okay, yeah, something.
This is full of Young diagrams, and you get one base that this is just monomials that are differentiated. So I don't know, maybe there is a class of interesting functions. And also, it comes from Hamiltonian operators. This paper by Gelfand, Dorfman, 79. So this is physics.
Yes.
Good.
You see, all these people, the mathematicians, maybe once I told you a good job that there are two kinds of mathematics, because in Bulgarian, Russian, German, Italian, Portuguese, mathematics is in singular, in feminine.
Yes.
In German, this is the mathematic.
In French too, yeah.
Yeah, but in French, this is the mathematic in plural.
Yes,
In Spanish, this is also the last mathematics in plural.
yes, yes.
In English, something between mathematics is. But there are two kinds of mathematicians. One of them claimed that there is one mathematics, including mathematics, for example, all these people in the Novikov said that they are mathematicians doing one mathematics. But there are some people who do, they are many mathematicians, many mathematics, they do their own mathematics. The third